So in this chapter, we go from describing correlation qualitatively. So we've talked about strong and weak and moderate correlation, positive or negative, but we haven't really been able to describe this in numbers or in math. So now we're going to start describing correlation quantitatively and giving it a number value. Now, let's see. I'll make a new note here under chapter 6. All right. So we'll call that measuring correlation. Yeah. Now, we can I mean, there is a method for finding a good estimate for a regression line. So if you have a set of data points like this, you can find their values in a table. If you find the coordinates for each point, you can represent that in a table. And you can find the mean value for each variable. So the mean of the x's, and we can write that as x bar. So this bar on top of the variable means the mean value or the average value. So the average of x and the average of y. And once you've found the mean value for both, you can represent that as a point. It's not really a part of the data set, but you can still draw this as a point, and maybe it's here. So this is how you find what we call the line of best fit. And the line of best fit, the starting point is that you find the mean of each data set or for each variable. And then we represent this as a point in the scatter plot. So up here, we have all these red dots, and they are actual data points. The green dot is not a real data point. It's just the mean of all the other ones. But once we have that mean, we're going to use that as a starting point for our line. So a line of best fit, it has to go through the mean. And other than that, we just try to have an equal number of points above and below the line. So maybe something like that. That's a line of best fit. There are possible solutions here. There's more than one solution, perhaps. So you know, it's something that we just use our intuition to draw. But the main principle is that the line is close to all other points with roughly as many above as below. So the regression line is a more exact alternative to the line of best fit. We're still going to use a scatter diagram as a starting point. But we use the regression line to find or to estimate, to put a number on the correlation between two sets of data. And the name of this, this regression line is going to be a straight line, and the measure of its strength is a number between -1 and +1, and it's called Pearson's product moment correlation coefficient. It's a very long name, so we're going to call it R instead. And this R value is going to be important. And we're going to learn how to interpret it. So on the calculator, we can easily estimate this value of R once we have the data. And we'll look at an example afterwards. But let's see. Yeah, R is it's a number or a numerical value that indicates the strength of the correlation. Now this only applies to linear correlation. But if R is equal to -1, we have what we call perfect negative linear correlation.
Olav, I can't see the OneNote.
Oh, let's check that again. Let's see. What about now?
Yeah, there it is. Thank you.
Okay, yeah. So R indicates the strength of the correlation. If R is equal to 1, we have perfect positive correlation. And this is a common mistake that students make if they see that the correlation is negative or the R value is negative, close to -1, they might think that this is a weak correlation, but it's actually very strong. It only means that the line goes downwards rather than up. So it looks like this, whereas positive correlation looks like that. And it doesn't really have anything to do with the tilt or the slant of the line either. But it's about how spread out the data points are. If you have an R value equal to 0, you have no correlation. So there's no pattern, there's no connection between the variables you're looking at. So, for example, if you have an R value of 0.9, this is a strong positive correlation. When we calculate the R value for a correlation line, we get this, we get this R value. We also get R squared. And the squared number can help us interpret the number, the R value that we find. So R squared, if our R was 0.9, then R squared would be 0.81. So what we can say that is the model explains 81% of the differences between the variables, or the not the differences, but the 80%, 81% of the variation, which is quite good. So that's the reason why 0.9 is a strong positive correlation, whereas 0.7 is much weaker than 0.9, even though it doesn't look like it. But that only explains 49% of the variation. Right. So a bit of explaining of this awkward name. This word product refers to multiplication of the variables x and y in the two data sets. And x and y is also adjusted by the mean. So when we calculate this R value manually, we take each x value and then we subtract the mean value, and then we multiply that with the y value, where we subtract the mean of the y value as well. So this is what part of the formula will look like. The word coefficient means that, well, simply put, coefficients are numbers rather than a variable. And this person's coefficient is a number value. It's not an x or a y. It's just a number that tells us the strength of the correlation. So R is a number made by a relationship between something called covariance and the standard deviation of each variable. So I should say something about covariance as well then. Covariance. So covariance it's a little bit difficult to explain, but it's useful and it's something you need to know possibly for your exploration if you do a statistical math exploration. So the covariance of two data sets, or for two variables, has the following formula. And we write the covariance as S and then X, Y as a subscript here, implying that this is not standard deviation, but this is the covariance, and we put both variables down here. And it's the sum of the product, or all the products of these x values where we subtract the mean every time, and then we do the same with the y values like this. So x bar and y bar means the mean value, so it's the average. And we're going to count these data pairs all the way up to n, so depending on how many pairs you have. And we divide the whole thing by the number of data pairs. So n is the number of data pairs. We'll look at an example soon. Yeah. So the x's belong to one data set, the y's belong to the other data set, and the x's and the y's, they make up these pairs, and the sets together have n pairs. And so this is part of the formula that you'll need next year. Because R is found by taking the covariance and we divide it by the standard deviation for x and the standard deviation for y. So this is the standard deviation for dataset y. And this is the standard deviation for dataset x. And again, this is the covariance. So, we have to flip back to chapter 3 or whatever it was to again find the standard deviation. But that looks like, let's see. So we have the standard deviation for a variable. Sometimes it's written like SD, or on your calculators it might come up as a small sigma, this Greek S. So this is going to be the same as Sx then in our formula here. But Sx is equal to the square root of the sums of all the x's, and then we subtract the mean, and then we square it. And we also divide by the number of x's. And this is going all the way up to n values of x. And we do the same thing for y. So this is going to be the sum of all the y's minus y bar. We square that and divide by the number of y's. And then you can put it all together. When you do this manually, I would advise you to use Excel. So we're going to look at that later. But this is the main formula that you're going to use, and you also need parts of it to explain what you're doing. So for our purposes now, we can find the correlation coefficient R on the Casio. But it's very important that we always look at the let's see, an R value close to 1 or -1 does not automatically mean that you have a strong correlation. We only calculate the R if we can actually see and confirm a strong correlation or a correlation at all in the scatter plot. So we always have to study the scatter plot first. So always investigate the scatter plot first. And this is very important. So do not calculate the R value unless there is a clear indication from the scatter plot that you do indeed have linear correlation.